All right, so last time we had talked about the two-particle system, and in particular the translation operator for it. Okay, so translation operator, two-particle system. And let's just summarize the information we had obtained. So one is that if you take the translation operator dagger and you act on a momentum operator for one of the particles and then act with TA, you get back P1. And the same thing for the other particle. Okay, so independently, we can translate the two momenta. And we had also noticed that if you do the same thing for the difference in the position operators for the two particles, you get back the same thing. But it's not true of the sum of the two particle positions or for the two particle positions independently. In any case, those three statements are equivalent to the statements that the total momentum commutator with each of the individual momenta is 0. This is the infinitesimal version of the left-hand side, or the left set of equations. So all those things commute. Okay, and the P's are the generators of the total translation. These are Hermitian operators. Okay, and P is by definition P1 plus P2. Whereas the T's are the unitary operators that do the translation for you, that do a finite translation, as opposed to infinitesimal. Okay, so one thing we can do with this set of information is we can construct a Hamiltonian that is invariant under translations. And so let me write that down. We can construct a Hamiltonian as P1 squared over the twice of the mass of particle 1 plus P2 squared over twice the mass of particle 2 plus a potential, but not just any potential. The potential is going to be a function of the difference in the two coordinates of the particles, those two operators. Okay, and this is invariant under translations. Okay, so first of all, the P1 squared and P2 squared, those are just defined to be P1 dot P1 for P1 squared. That's the definition. And therefore, according to this statement right there, or this statement, that part of the Hamiltonian is going to be invariant under translations. The same thing for this. And then the potential here is an energy of interaction that's only dependent on the distance between the two particles, not where they are individually. So if I have a particle 1 there and a particle 2 there, that's R1 minus R2. And so if I shift the whole system by moving both the particles by the same distance, by the same vector, nothing will change. Okay, so then this set of commutation relations here ensures that this Hamiltonian will be invariant under translations. And so that means that TA dagger, Hamiltonian TA, is going to give you back the Hamiltonian, or equivalently, the momentum operator, total momentum operator, commutator with a Hamiltonian is 0. So we've managed to construct a Hamiltonian that's invariant under translations, and this is very non-trivial because for a single particle, that would be very hard to do, except there's one case where you can do it, and that's if it's a free particle. But having a single particle that's invariant under translations with a non-zero potential is essentially impossible. But once you have more than one particle, by having the interactions between them be of this form, then you can have a Hamiltonian invariant under translations. Okay, so if we added, and there's nothing wrong with doing this, but if we added, say, a potential that only depended on the position of particle 1, or a potential that only depended on the position of particle 2 to the Hamiltonian, it would not be translation invariant. Okay, so that would mean, among other things, that we could not find simultaneous eigenstates of the total momentum and the Hamiltonian. Okay, now we can do the same discussion for parity for a two-particle system. So first of all, we should define what parity for a two-particle system is. And I can do that by telling you how it acts on the eigenstates of the system in any basis. A good basis to use is the position eigenstate basis. So the parity operator acting on a ket that describes particle 1 being at position R1 and particle 2 being at position R2 is, by definition, the ket where I've flipped the positions through a mirror, minus R1 and minus R2. And then from that, it follows that if I do pi dagger, which is really pi, R1 pi, that's equal to minus R1. And pi, I won't even write the dagger this time because pi equals pi dagger. This is minus R2. There's no infinitesimal version of these because you can't do an infinitesimal part of a parity thing. But you can do the same thing for the momentum operators, P1 and P2. Okay, and then if you look at the Hamiltonian that we wrote down, okay, then pi dagger, I'll write it as pi dagger this time for variety, Hamiltonian pi is equal to the Hamiltonian. And so the Hamiltonian is even under parity. Okay, so that's for a two-particle system. More generally, suppose I have n particles. And then we can write down a Hamiltonian that's invariant under translations. And the way to do that is just, first of all, write down a bunch of kinetic terms, one for each particle. So I'm summing over j that labels the different particles, pj squared over twice each one of their masses. And then I write down a whole bunch of potential terms. I'm going to be summing over two labels, and I'm going to enforce that j is less than k. And then there's a potential between every pair of particles, and they can be different potentials. So they're labeled by both indices j and k. And then I'm going to make this dependent on the magnitude of the distance between the two particles. Okay, so the reason I don't sum over j larger than k is that would be redundant. Once I'm considering every pair of particles, I can write down what the potential is between them, their energy of interaction, and then I don't need to repeat it for j greater than k because it would just be another contribution to that same interaction energy. Okay, so this is invariant under translations. I'm just stating that this is true because the algebra is pretty much the same as what we did for two particles. Okay, but first I should tell you what the translation operator is, and it's just a nice generalization of the two-particle case. It's the exponential of minus I, A, the vector, dotted into the sum of all the momentum operators, all divided by h bar. Okay, and so the sum of all the momentum operators is the total momentum. That's just the definition. And so that's what goes into the translation operator. So then, just like we did for two particles, TA dagger, Hamiltonian TA, gives back the Hamiltonian. Okay, and so that makes it invariant under translations. It's also invariant under parity. Okay, and there we need to define, first of all, what parity is. The parity operator acting on any state where all the positions of all the particles are known is going to give back minus the ket with all the positions multiplied by -1. Okay, so something like that. And so then you can show that pi dagger h pi is again h. Okay, and h commutes with the total momentum operator. Okay, and so now that's a way of constructing a multi-particle Hamiltonian that's invariant under translations and parity. So one thing to note is it's not invariant under translations of just individual particles, which you can define. There's nothing wrong with defining those. So under translations of just one particle, so for example, here's my translation operator for particle 1 is I just do the exponential, but now I only include the momentum of particle 1 in the exponential. Okay, so this translates only particle 1. But that's not a symmetry of the system. Okay, so because it doesn't translate the others. And so T1 A dagger, Hamiltonian T1A. I guess I should put harpoons on all these. These are all vectors. This is not going to give you back the Hamiltonian. Okay, so H is not invariant unless you just set all the potentials to 0, which would make you have the free particle back again. So that would be not terribly interesting. Okay, so given the Hamiltonian and the total momentum operator and the parity operator, you notice that they are compatible observables. If the Hamiltonian is, as we're assuming, of this form right here. Okay, so H, P, and the parity operator are compatible observables, or commuting observables. But for future reference, I want to mention that they are not a CSCO. And the reason they're not a CSCO is they don't have the first C. They're not complete. In order to make a CSCO, you need more operators. You need to actually include the total angular momentum operator.
sorry, Professor, forgive my shortcoming. I forgot what CSCO stands for.
CSCO is complete set of commuting or compatible observables. Commuting and compatible mean the same thing. Okay, and so the complete is what's not working here. Okay, so that's a story for another day of including the total angular momentum also, but I just wanted to mention that. So even though they're not complete though, it does mean that we can find an orthobasis of common eigenstates. And so just to write down what they would look like. Okay, they would be labeled by the energy and by the total momentum as a number and by the parity as a number, which is either plus or minus 1. But then because it's not a complete set of commuting observables, I might need other labels. In fact, I almost always will need other labels to distinguish them. That's the ... here. So this is for, these are stationary states. Okay, eigenstates of the Hamiltonian. But more generally, another consequence of the fact that they're compatible observables is that for any state, regardless of whether or not it's a stationary state, so let me call that psi, the time derivative of the exponential of the total momentum operator is 0. And that was Ehrenfest's theorem in action. Okay. So that's one of the reasons it's nice to identify compatible observables, is so that you can make statements like this and so that you know in advance what sort of stationary states you're looking for. When we did the square well and the particle in a box, we sort of naturally found that those were eigenstates of parity, but because parity commuted with the Hamiltonian. But all of this explains why it's sort of guaranteed to happen.
So
okay.
Professor, I'm sorry, stationary states doesn't necessarily mean eigenvalues, correct? Eigenfunctions, correct?
Stationary states means it's an eigenfunction or an eigenstate of the Hamiltonian.
Oh yes, okay.
Okay.
Thank you.
That's just the definition. They're literally synonyms. There's no, sometimes physicists like to have 3 or 4 different words for the same thing, and this is an example. All right, so we will come back to angular momentum as a transformation, a unitary transformation. But since we're not going to be doing things with angular momentum for a while, we'll just move right on to the harmonic oscillator. So we'll start with the harmonic oscillator, and then we'll continue after the midterm. Okay, which I'll just abbreviate usually as HO for harmonic oscillator. And so let's talk about it classically first. So we have some base of operations with a spring attached to it, and there's a mass m on the end of the spring. Okay, and this thing is able to move back and forth. We'll just say in one dimension, and there's no gravity or air resistance or anything like that. So the kinetic energy of a mass in terms of its momentum is p squared over twice the mass. And there's also a potential energy associated with the spring, which we can write as 1/2 m, an angular frequency squared times x squared. So that's our potential. Notice it's even. So this is going to be even Hamiltonian. Omega has units of 1/time. Okay, and the classical force on this mass is minus the x derivative of the potential, which is minus m omega squared times x. The fact that there's a minus sign means it's a restoring force. Okay, and it's proportional to the displacement. These are the hallmarks of a harmonic oscillator. Okay, and we can also write this as minus k times x, where we've just defined omega in terms of k and the mass. So omega is defined to be square root of k over m. Okay, so for future reference, let's review how the harmonic oscillator works in classical mechanics. So first of all, our Hamiltonian is just the sum of the parts. It's p squared over 2m plus 1/2 m omega squared x squared. And then, as you should have learned or will learn in a classical mechanics class, you can do the Hamiltonian equations of motion. And for a general system, so this is classical. For a general system where you're given some Hamiltonian that depends on a bunch of coordinates, I'll call them q sub I, and their corresponding momenta p sub I, where I runs from 1 to n. In the present case, n is just 1. The Hamiltonian equations of motion are that the time derivative of each q is equal to the partial derivative of the Hamiltonian with respect to the corresponding momentum. And the time derivative of each momentum, the dot is the time derivative, is equal to minus the time derivative, or the derivative of the Hamiltonian with respect to the coordinate, q sub I. Okay, so those are just general statements. And in this example, x dot is equal to partial h partial p, which is equal to p over m. And p dot is equal to minus partial h partial x, which is minus m omega squared x. Okay, and so what we have is two coupled first order differential equations. And if we take the time derivative of the first one, of the first equation, put it into the second equation, then what we're doing is we're uncoupling the equations at the cost of making it one derivative higher. And so our equation becomes x double dot is minus omega squared x. And then the solution is x of t is equal to x naught cosine omega t plus phi 0, and p of t is equal to minus m omega x naught sine omega t plus phi 0 for some phi 0 and some x 0. Okay, so this is the general solution. And so one thing we're going to want to do eventually is find out, how does quantum mechanics give you something that reproduces this classical solution in some limit? We're going to first solve for the stationary states, but it turns out the stationary states do not give you this sort of classical behavior. And instead, we will have to construct something called coherent states. Coherent states are the things whose expectation values obey these classical solutions. Okay, so that's something to look forward to after we've done a thorough study of the stationary states, which are the more quantum mechanically relevant things. Okay, so that's just the classical overview. One thing we should mention is, why do we bother with the harmonic oscillator? And there are many reasons. But probably the best reason is just the fact that many more complicated problems reduce approximately to a harmonic oscillator. So let's go over why that's true. So many problems are roughly equivalent to multiple harmonic oscillators. Okay, and the sort of, let's start with just one harmonic oscillator. And that's often a solution or an approximate solution to a more general potential where I pick out some special position x0, which is sort of the equilibrium position of a particle or some other quantity of interest. And I write down a potential. And maybe it has some form like that, some arbitrarily wiggly shape. But the point is, if you're lucky, you can write the potential as a Taylor series expansion of the function that we've drawn there. So let's see how that goes. If I have v of x, and I do a Taylor series expansion about x0, it looks like this. Okay, first there's the constant term, then there's the term that involves the first derivatives of the potential, evaluated at x equals x0, times a linear term. Then the second term is 1/2 x minus x0 squared, times the second derivative of the potential, evaluated at x equals x0. And then there's a 1/3 factorial, times the cube of the difference, times the third derivative. And this goes on forever. Okay, now let's think about these three terms in turn. The first one is a constant. And so now we can argue that doesn't matter. So recall that in Hamiltonian time evolution, in a quantum system, the unitary operator is u of t equals e to the I h times t with an h bar. And so the point is the constant part of the Hamiltonian just gives you an overall phase, and it gives you the same overall phase to all states. So constant part of Hamiltonian gives same overall phase to all states. And we know that a common phase, constant phase, is not observable. It would be different if this were a different constant for different states, because then we could construct some sort of matrix element involving an interference between the different states and observe the phase. But this is literally just a constant here, and so it doesn't matter. Okay, so we can ignore that. The next term we can ignore just because we're assuming that x0 is the minimum of the potential. That means, by definition, the first derivative of the potential there must vanish. Okay, so x equals x0 is equilibrium, a stationary point. Okay, so we can also ignore that term. And then this term involving the cubic parts, we're going to ignore because we're going to assume this is small. And in fact, we're going to assume all the other terms are smaller too. So that would make sense if the difference between x and x0 stays small, because we're cubing a small number and then we're taking the fourth power of a small number. Okay, and so the only term left over is this one, the quadratic term, which is the harmonic oscillator term. Okay, and to see that, we just redefine coordinates. Okay, and so we do that by saying, let's take x and replace it by x plus x0. Then our potential, ignoring all the terms we said to ignore, is just approximately 1/2 second derivative of the potential at that point times x squared. Okay, but this is just some number, and so we define this to be m omega squared. That's just really defining what omega is for the system. Okay, and so from that, we get that in any system that obeys these properties of being able to expand in a Taylor series and being able to drop small terms is approximately a harmonic oscillator. All right, now that was in one dimension, and in 3 dimensions, things are a little bit more complicated, but in the end, everything works out the same. So let's go through that. So in 3 dimensions, you can now take a potential that depends on 3 coordinates and again expand in the Taylor series. So first of all, there's going to be, I'm going to assume the minimum of the potential is at 0, 0, 0. Otherwise, I would shift my coordinate system to make it true. And so there's a constant term. There's a term involving first derivatives, but now I have to do a sum over the coordinates x sub j times their respective first derivatives, where I've evaluated all of these at 0. So xk equals 0. And then I have a 1/2. Now I have to sum over j and k independently, each one from 1 to 3, because there are 3 coordinates. And so then there's xj, xk times a second derivative, which I'm going to write as vjk. And then more terms, but again, I'm going to assume those are small. So these are small.
Dr. Martin?
Yes.
On the second term, why is it x sub k equals 0?
So that just means that the reason I write x sub k here instead of x sub j is I'm taking a derivative with respect to x sub j, but then that function could also depend on other x's besides the one I took the derivative with respect to, xj. And so this is just saying set them all to 0, not just the one you took the derivative with respect to.
Okay.
Okay?
Thank you.
Good. Yeah, that's a good question, because otherwise you, well, so yeah, again, this thing could depend on all 3 of the x's, but I'm taking a derivative with respect to one of them. And then after I take the derivative, then I set all the x's to 0. Okay, good. So this first term's a constant, so just as before, we're going to ignore it. This term here is small. This thing is actually going to be 0 for the same reason as before. If it's not 0, then we're not at a minimum of the potential. At an extremum, whether it's a minimum, a maximum, or a saddle point, these are all by definition 0. Okay, so this equals 0 at the minimum. And what can we say about this term, this last term here? This is a matrix of second derivatives, and second derivatives with respect to x's commute. So whatever that thing is, it's a symmetric real matrix. So V sub jk, first of all, its definition is this, just the way we constructed it from a Taylor series. Okay, this is a symmetric real matrix. We're not allowing the potential to be complex or anything weird like that. In the real world, potentials are real. Okay, and so it doesn't matter which order you take the partial derivatives to, or derivatives in. Okay, so now the thing that's going to allow us to make this into, notice that this looks like these different coordinates are coupled together in some arbitrarily weird way, but that's actually an illusion. They're not, we can uncouple them because of the following theorem in linear algebra. Okay, you can diagonalize a symmetric real matrix by an orthogonal matrix. So it can be diagonalized by an orthogonal matrix. And so what that means is, let me just call this matrix here V, then V is equal to the transpose of an orthogonal matrix, that's an O, not a 0, times another matrix I'm going to call V tilde times O, where V tilde is a diagonal matrix. So it's equal to the diagonal, where the entries on the diagonal are a set of numbers, V tilde 1 up through V tilde n, for n equals 3 in this case. Okay, so here, this is an orthogonal matrix. And V here was the matrix. It's not the original potential, it's the matrix whose entries are V sub jk. So I'm using maybe a not great notation where V actually stood for the original potential here, but that's not what this V is. This V is this V. Okay? So another way of writing those things is that, oops, V sub jk is equal to orthogonal matrix transpose V tilde diagonal, so it only needs one index, and then orthogonal matrix again. So the fact that it's transpose is, notice I've written, normally if I'm going to do matrix multiplication, this n should be next to this n, but I've reversed the order here to make it a transpose. Okay, so now what can we do with that? Now we can write our potential as a function of x, y, and z, or x1, x2, x3. It's going to be our irrelevant constant plus sum over ijk of 1/2 orthogonal matrix Ni, oh, sorry, I need to go back here. Orthogonal matrix Ki, Xi, V tilde n, orthogonal matrix Kj, Xj. Okay, and then there's plus small here. Okay, now to make this nicer, what we're going to do is we're going to take this right here and define it to be a new coordinate, which we're going to call x tilde of k. So we're going to define x tilde of k is sum over, let's call it L, equals 1 to 3 of our orthogonal matrix KL times x sub L. And we're going to do the same thing for the momentum. So P tilde K is sum L equals 1 to 3. We're going to use the exact same orthogonal matrix for the P's, for the momenta. Okay, and then from this, one can show that, actually, let's go ahead and do it. If you take the commutator of, let's say, P tilde n with x tilde m, that's equal to, we can just use the definitions, sum k equals 1 to 3, orthogonal nk, sum j equals 1 to 3, orthogonal mj, of the commutator of the original pk with the original xj. So I've just plugged in these definitions here. And notice when I'm taking a commutator here, I'm not taking a commutator in a matrix sense. I'm taking a commutator in an operator sense. So the O's are just numbers. They're just some array of numbers. They don't commute or have any commutation properties. This is a operator commutator. Okay, and this is equal to minus I h bar delta jk. And that means when I do my double sum, only one term in the, say, j sum will survive. This becomes minus I h bar sum j equals 1 to 3. Only one term in the k sum survives. And then I get orthogonal mj, orthogonal nj. Right? I set k equal to j. But this right here is the matrix O transpose, the Mn component. And by the definition of an orthogonal matrix, that's the Kronecker delta, delta Mn. Okay, so what we've shown is that the new tilted momentum and position satisfy the same commutation relations as the old one because of the Kronecker delta. So that's good. That means the tilted momentum and position are the same or just as good as the untilted ones from that point of view. Also, you can construct the following thing. Let's say I do sum n equals 1 to 3 of p tilde n squared. If I plug in the definition, that's going to be a sum over n, j, and k of orthogonal matrix nj, pj, orthogonal matrix nk, pk. And now if you do the sum over n, okay, the sum over n doesn't involve pk and pj, so we can just pull them out. Okay, and so the sum over n involves this quantity, n equals 1 to 3, O nj, O nk, which is now again O transpose O, the jk component, just by the definition of matrix multiplication, which is delta jk. Now I take that and I plug it into the original sum here. And it says the only term that survives is when j equals k. Okay, and so my sum n equals 1 to 3 of p tilde n squared is sum over j and k, delta jk, pj, pk, which is the same thing as the sum j equals 1 to 3 of pj squared. Okay, so what that means is we can take in our original Hamiltonian the sum of the momenta squared components and just replace them by the same things with tildes on them. And so what we've learned here is that our total Hamiltonian is just 1 over 2m times a sum from n equals 1 to 3 of pn tildes squared plus 1/2 a sum from n equals 1 to 3 of v tilde n's times x tilde n squared. Okay, and that is the sum of 3 one-dimensional harmonic oscillators. Okay, so if we can sum the one-dimensional harmonic oscillator, we can solve for a three-dimensional harmonic oscillator. And not only that, but we can solve for a general potential that's close to a harmonic oscillator in shape. Now, the fact is that because these are all different numbers in general, there's no guarantee that they're the same number. They're going to be 3 different natural frequencies, one for each of the different harmonic oscillators. And so this is called, in general, the anisotropic meaning not isotropic, 3D harmonic oscillator. But it's equivalent to 3 one-dimensional harmonic oscillators. Okay, and then there's this great quote from Sidney Coleman, who said, "The career of a young physicist consists of treating the harmonic oscillator over and over again in ever-increasing levels of abstraction." I mean, it's just sort of a whimsical way of saying that you can go ahead and expand any potential you want pretty much, and it's going to look like a set of harmonic oscillators as long as you can ignore or treat as small higher order terms. But there are some exceptions to this, because there are some cases where the Taylor series expansion doesn't work. So one is the free particle. In the free particle case, there's no restoring force at all. And so you can't treat it as if it were there. But that's okay, because we know how to do the free particle. Another example is the case that we've already done with a square well. Or its extreme example, the particle in a box. Okay, and that's because the Taylor series expansion for a square well just doesn't work. Okay, and then there's a third class of examples that includes things like the hydrogen atom. So the problem with the hydrogen atom is that the minimum of the potential, V0, is actually not a constant finite number. It's actually negative infinity. So the moral of the story is there are some examples that you can't treat this way. There are exceptions, but these are all sort of classic things that you should know how to do. And so if you know how to do the free particle, the square well, the hydrogen atom, and the harmonic oscillator, then many other systems are approximations to one of those sorts of problems. Questions on that? Okay, so let's do one more thing, and then we will take up the harmonic oscillator in after the midterm. So let me just make the claim that all stationary states of a harmonic oscillator have positive energy. Which is an eigenvalue. Okay, and here's the proof, which is sort of 2 lines. The energy eigenvalue for a stationary state is certainly going to be equal to the expectation value of the Hamiltonian. That's the expectation value of p squared over 2m plus 1/2 m omega squared x squared. And so we can split that up into 2 parts. There's the expectation value of p squared times 1 over 2m plus 1/2 m omega squared times the expectation value of x squared. Okay, and so heuristically, we're taking the expectation values of squares of Hermitian operators, which should be positive. In fact, let's see exactly how that works. So this is equal to 1 over 2m of the inner product of the state p psi with p psi. So what have I done there? I've used the fact that P acting on psi is by definition the state p psi. And then the bra psi with P on the right is equal to the conjugate, the Hermitian conjugate of p psi. So it's p psi dagger. Okay, which is p psi because it's a Hermitian operator. Okay, so that's where we get the crucial fact that it's Hermitian. And then I could do the same thing with the x, because x is also a Hermitian operator. So this is the inner product of x psi. Okay, but it's one of the postulates of a Hilbert space that the inner product of anything with itself is a positive number. So these are both positive numbers. And so the whole thing is greater than or equal to 0. And really, you can't have 0 because it would be the null state. Okay, so even without doing any quantum mechanical calculation, we've shown that the energy eigenstates of the stationary states of a harmonic oscillator have to be positive numbers. In fact, I should really erase the equals, because if it was equals, that would make it a null state, which we don't care about. Okay, so that's it for now. Reminder, of course, that you have a midterm on Monday. I may or may not be there. I'm supposed to find out after 5 o'clock tonight whether I have to show up for my jury duty summons. I hope I can make it, but if not, somebody else will be there to proctor the exam. It's in 121 Davis. So let me go back to the midterm rules, which were posted on the course webpage. So again, this is the room. I have never actually been in that room, but I'm assured it's a large room. It's next door to La Tourette. It's the building with the observatory on top. And then one other thing that I should point out is I'm changing one of the rules, which is that originally I said I would provide for you this set of formulas. And I'm not going to do that, because now that I've written the exam, I realize that none of those formulas can possibly help you. Okay, so this won't help.
We don't need to print it out either, correct?
You don't have to print it out. Those formulas will not be useful for you. And if you want, you can take that as a hint as to what might be the content of the exam. But it would be silly, I think, to ask you to print it out or to give it to you when it turns out, now that I've written the exam, those formulas won't help you. Okay, on the other hand, you should definitely bring your own notes of your own choice of things that you think will help you, which you should do by going over the homework. Okay, and the homework 5 is due today. And so I will count it as on time if I wake up tomorrow and find out that you've emailed it to me. So as long as it gets to me by 9 a.m. on Saturday, then it will be on time. I say that I don't really encourage everyone to pull an all-nighter, but hope you get it done today. But in any case, whatever's there when I wake up tomorrow morning is considered on time, and then I will email you the solutions for homework 5 so that you can study from them. Everybody should have already received all the solutions for homeworks 1 through 4, as well as your graded versions. So if you haven't, let me know, and I can send those to you. All right, any other questions on this? If not, then I or my proctor will see you on Monday.
Professor, I
Yes.
got some questions on the homework. Do you have time?
Yeah, sure. Let me stop the recording, I think.